All right, now let's go to step 4a. Right? Once we've calculated the chi-squared test statistic, we want to use that test statistic to make a decision. So we can either calculate a probability or p-value based on that chi-squared test statistic, or we can compare that test statistic with a critical value. Even though we're working with a different test statistic and a different probability distribution than before, the underlying mechanics are the same. Meaning, we reject in cases in which we have a very extreme chi-squared test statistic. That is, we reject the null. In general, if the chi-squared test statistic is greater than or equal to some critical value based on alpha, then we reject the null that the population proportions are the same as the claimed proportions in the population. Right? We just reject the null. How do we find this critical value, which we call chi-squared with a subscript alpha, referring to the alpha criterion level? Well, we can use tables, but typically we will use modern statistical software. Again, the critical value depends on the level of alpha as well as the degrees of freedom, because the degrees of freedom, that is effectively the number of categories, because it's just the degrees of freedom is k minus 1, that governs the shape of the chi-squared distribution, which can affect and it does affect the critical value. A technical note you should keep in mind is that the chi-squared test is based on a two-sided alternative. However, the rejection region is in the right-hand tail. This is because if an observed cell count is either above or below the expected value, they both lead to large calculations in the chi-squared test statistic. That is, that chi-squared test statistic will be in the right tail. Okay, that's just a technical note, and that really just reflects the sort of fact that the chi-squared distribution model is from 0 to positive infinity. Let's look at different critical values for the chi-squared test. So if we have alpha of 0.05, so we're just fixing our alpha criterion level, which is the standard level in the social sciences, you can see that the actual critical value, the chi-squared subscript alpha, that changes. Okay, this is the benchmark by which we evaluate our chi-squared critical value. Right? So our chi-squared test statistic. So you can see that if we have 3 categories, or similarly 2 degrees of freedom, then the chi-squared alpha, that critical value, is about 6. Right? As we increase the number of categories, as our degrees of freedom increases, that critical value increases as well. Right? The key point here is that if our chi-squared test statistic lies beyond, right, equal to or beyond that critical value, we will reject the null hypothesis. We can also calculate probability or p-values, just like before. For the chi-squared test statistic, the p-value is simply the probability of obtaining a chi-squared test statistic greater than or equal to the one we actually observed. Just to keep in mind in notation, we, that sort of big X, that sort of square-looking X, that's just a capital letter for chi. That's capital Chi and lowercase chi. The key point here, just for the purposes of calculating p-values, is that if that p-value, if the probability value is less than or equal to alpha, then we reject the null. Where the null, for the chi-square one-way goodness of fit test, is that these population proportions are equal to the claimed proportions in the population. Typically, we'll use statistical software to calculate p-values. And again, there's this other technical note, because the chi-square test statistic, it's based on a two-sided alternative, right? Because the alternative is simply, it's not, the idea of the alternative is simply that these claimed values in the population don't equal at least one of these actual values in the population. It's a two-sided test. However, the p-value is based on a one-tailed rejection region. Again, this is because if an observed cell count is either above or below the expected value, the expected number of counts, they both lead to large calculations in the chi-squared test statistic. So here's an example in which, suppose we had a set of data and we calculated these observed and expected counts, and we calculated a chi-squared test statistic of 4.5. And we had 4 categories. So our effective degrees of freedom is k minus 1 or 4 minus 1 equal 3. Right? The degrees of freedom governs that kind of shape of the chi-square distribution. You can see the chi-square distribution is sort of normal. That reflects the, it's kind of pulled towards the positive region a bit. And you can see that our chi-squared test statistic is right there, and the p-value is simply that region greater than or equal to our chi-squared test statistic. So the p-value, the probability of obtaining a chi-squared test statistic as a more extreme than the one we observed, under the assumption that null is true, under the assumption that the proportions of the population equal the claimed proportions in our hypothesis, that p-value is 0.212. Right? That's a larger probability value than 0.05. So in this particular instance, we would fail to reject the null hypothesis. Again, what we're doing is just like before, where we calculate critical values and p-values using our test statistic. Finally, based on these decisions, you either reject or fail to reject the null. It is important, of course, never to stop here. Always interpret your conclusion, because with the chi-square one-way goodness of fit test, it really relies on this claimed distribution of the population. Suppose somebody's making a claimed distribution of the population that just doesn't make any sense. It just has no sort of face validity, or just sounds absurd initially. You might reject that claim, but maybe it's not that important. Maybe it's not that substantively interesting because that claimed distribution of the population is not taken seriously by anyone. So always keep that in mind. To put it another way, you might say statistical significance, getting a low p-value or a very large chi-square test statistic doesn't necessarily mean that your findings are substantively important. Again, ask, does the null hypothesis make sense?